students, my name is Siddharth Patra. I am an assistant professor in the Department of Mechanical Engineering, and today we will be doing tensile test in this instrument. This one is called universal testing machine. If you are not already familiar with this machine, this machine can perform various type of tests, hence the name universal testing machine. For example, you can perform a bending test over here by putting a beam sort of a structure simply in a simply supported fashion, and then we can load it over here. So few things about this instrument over here. There is a fixed crosshead and there is a moving crosshead. So in which the tensile test will be done between these two crossheads. So the specimen would be fixed to would be attached to both the fixed crosshead and the moving crosshead, and then the fixed crosshead would remain stationary and the moving crosshead would stretch the specimen. So in this case the specimen is a cylindrical specimen. We'll show you that specimen in a minute. So that can be pulled down using the moving crosshead, and thereby the specimen would be under tensile load. And the two important things that we are supposed to measure here is the amount of elongation versus the amount of force applied, or the vice versa. Now this machine is run by a hydraulic system. So you can see all the circuitry over there, and this is the controller. This is where you can control the amount of elongation or amount of loading, and you can also read the data from here. So for example, you can get the reading of how much force that is being applied over here from this dial, okay, and also you can adjust the maximum. So the unit of force is in kilonewton, okay. So right now it has been at is it okay. 0.5 na? Okay. So that it is the least count, right? So so this one is a least count, 0.5 kilonewton, and the maximum value of the force is 100 kilonewton. Okay, and this can also be changed using this handle over there. And for example, now it has been changed to 20 kilonewton, the maximum value, and the least count being 0.1 kilonewton. Okay. And this one is again another scale with maximum value of 200 kilonewton and the least count being 1 kilonewton. So as you might notice, in this dial there are two pointers. Okay, the two pointers. So there are two pointers. Okay. So the one that is currently moving, the one which was initially stationary, there is used. Yeah. So the one that is moving, okay, right now. Okay. So that when that moves towards the in the clockwise direction, that actually pulls the one that was initially stationary. But then when the moving one moves towards the left, the stationary one becomes the second hand becomes stationary at that location. That means that gives you the maximum value of the force in the entire loading period. Okay, and that maximum value actually ultimately gives you the ultimate tensile stress. So there are two hands in the dial. One of them is for showing the instantaneous load value. The other one is for showing the maximum load value in the entire loading cycle. Okay. So now the specimen would be attached, and this is the specimen. This is called a dog bone specimen. It's a cylindrical specimen. Okay, and the total total length is about 350 millimeter. Okay, you might notice that the diameter of this part is slightly higher than this part. This one is about 10 millimeters and this one is about 12 millimeters. Okay, and this 10 millimeter diameter portion is about 160 to 180 millimeters. Okay, so that is kind of the effective length of the specimen, and this these two sides of the specimen which has the higher diameter, that is where the specimen would be held by the fixed and the moving crosshead. Okay, that's where it would be attached. The reason for making the two ends slightly higher diameter is that to ensure that the failure, when the material actually fails, the failure occurs in the central portion where the diameter is the lowest. Okay. So as we can see, this portion over here, this one is a lower diameter portion, and this lower diameter portion is our test region, and that, as I mentioned earlier, that is about 160 to 180 millimeters. And the two portions that are inside the two crossheads are that higher diameter portion, and as you may have noticed earlier, there is a taper between the higher diameter and the lower diameter. That actually is there for in order to avoid any amount of stress concentration. And the reason for making the higher diameter portions at the two ends is because we want to have, since this one is our test region, we want to have any type of activity, including any change in the shape or any fracture happening within this test region. And the way to ensure that is that this remains the lowest diameter region. This is uniform, of course, with a certain amount of approximation, but that is the lowest diameter in the entire segment. And this instrument over here, this is an extensometer. Okay, this is a spring-loaded extensometer, mechanical type. So so the way it is attached to the specimen is by by pulling it. So it is spring-loaded. You can make the gap higher by pushing it. Okay, and then we would place the specimen in the gap between these two. So these two rods are over there to ensure the gauge length. The gauge length is the gap between this knife edges, this knife edge. I hope you can see this one, this small knife edge over here, and this knife edge over here. And that gap in this case is 60 millimeters. And of course, you can move these two knife edges higher and make any different gauge length. But for this one, we have set it to be 60 millimeters. So 60 millimeters is our gauge length. Now I have mentioned three lengths. One is the total length of the specimen, that is about 350 millimeters. Okay, and this effective length, which is the 10 millimeter diameter portion, and in that 10 millimeter diameter portion also, we are only taking a very small segment of 60 millimeters. Now reason for doing that would be that from the higher diameter, that is the 12 millimeter diameter portion to 10 millimeter diameter portion, there is a taper region, and in that the stress state becomes three-dimensional. Okay, and it needs to have a smooth transition from three-dimensional to one-dimensional stress state. And actually the test that we are doing, okay, that is suitable for uniaxial stress state. So we are doing an analysis with uniaxial stress state. To ensure uniaxial stress state happens in the region of the bar, we are supposed to take 1/3 of the total length. Now the total length is about 180 millimeters, around 160 to 180 millimeters. So we will be taking only 1/3 of that length in the middle of the rod, which would be around 60 millimeters, and that's where we attach the extensometer. The least count for the extensometer, you might notice, is 0.01 millimeter. Okay. Now, how does the extensometer work? You see, when this one being spring loaded, when we attach the extensometer to the specimen, these two knife edges are actually in static friction with the surface of the surface of this rod or the dog bone specimen. And as the dog bone specimen elongates, the gap between these two knife edges also elongate. And how does that happen? You see, as this knife edge is these two lower knife edges, as they go down, okay, as the moving crosshead pulls the bar, the lower knife edges go down, and as they do so, they would push the reading on these two dials. Okay, they would push under these two these two dials. So therefore, you will see the reading of the elongation from this dial. Okay, and that's how the elongation is measured. Okay, and okay, so the thing is, so why do we need two dials over here? The thing is, it's a possibility that even with the extensometer attached to the bar, okay, one of the knife edges might lose contact, might not be in static friction with the might be in contact but not in static friction with the bar itself. Okay, and some slip may occur, and because of that slip, okay, one of the dials, and we do not know which one, okay, would not probably give you the correct result. Okay, of course there is a chance of both of them not giving you correct result. But then in order for this to be attached to the bar, which is only by means of friction, okay, one of the knife edges must work. Okay, so there is a possibility that both of them would show you correct result, or at least one of them would show you more or less the correct result. So while reading the data, if let's say one of them tells you it is 0.5 millimeter of elongation, the other one tells you 0.48 millimeter, then we can take the average of that. But if one tells you that it's a 0.5 millimeter of elongation, the other one tells you it is 0.25, you are supposed to ignore the smaller value. Okay, that's how we work with the extensometer. Now this extensometer would be attached to this rod over here. Okay, and then this this moving crosshead would be pulled downwards, and it would in a way stretch this bar over here, and therefore we would get the elongation data from the extensometer. Okay, and similarly we will get the value of the force from this dial over here. Not only that, here we would be actually plotting a graph. Okay, so as the loading happens, we would also be generating a graph. So the y-axis is basically the load in kilonewton. You see the maximum value is 100 kilonewton, and the x-axis, so it would be rolling in this way. So the x-axis would be your elongation. Okay, so the load versus deflection curve we will also generate from this through this graph as well. So now we'll attach the extensometer. So right now we just did was we adjusted the current reading of the extensometer to 0 for both the dials. Okay, so we get the measurement from 0 itself. Otherwise, we would have to subtract. Okay. Now the extensometer would be attached to the specimen. Okay. So here I have the instruction sheet, and the specifications of the test have already been written down over here. So, so first thing is the full length of the rod that I just mentioned, that is about 350 millimeters, and then the effective length, we already discussed what that is. That is the region with the 10 millimeter diameter. So diameter is not exactly 10 millimeters. So you can see we have taken reading at 3 different sections, okay, at 3 different heights and 3 different angular orientation, and from that we are taking an average. And here we have listed down the extensometer gauge length. Now so many lengths are there, and I just tell you that which one is important when we would be measuring the strain, because you see the uniaxial stress state is only there in the 1/3 of the total effective length, okay, which is 165 millimeters. So in that 1/3, that is the 60 millimeter gauge length, is where we would measure the strain. So this so the deformation that you would note over here on these two extensometer dials are the deformations over that gauge length. So essentially, in order to measure the strain, you would simply divide that value, that extension, with the gauge length, which is 60 millimeters, to get the value of the strain. Now there are some specifications with regard to the machine that we are working on, which is an universal testing machine, maximum capacity of 200 kilonewton, which we just showed you, and then these are the specification of the extensometer. So the range of working of the extensometer is 0 to 5 millimeter. Okay, so so once the deformation goes beyond 5 millimeter or tends to go beyond that value, you cannot use this extensometer, and least count is 0.01 millimeter. Now there are some other details over there. So these specifications must be there in your instruction sheet. Then we will be taking the reading. Okay, so this is there are some discussions over here, some of the experiment steps that are mentioned over here, and here are the procedures. Okay, and there would be some questions for you to answer in the end. But before that, this is the segment where you take the experimental data. While doing the experiment, you are supposed to note down the data over here, and from that data you are supposed to calculate various things. For example, the value of the load, that is the actual force in kilonewton while you reach the yield point, or what is the maximum value of the load, and other things. And from that you will calculate the stress value at the yield point, the ultimate stress value, that is the maximum load divided by the cross-section area, percentage elongation, and several other things. So here you see, one important information is mentioned, which is percentage elongation. Percentage elongation is a measurement of the ductility of a material, given material. What does that mean is the length before elongation, okay, and comparison between length before elongation and length after elongation. Okay, so the percentage increase in the total length. Now you see, once this specimen is loaded and then gradually it would extend, and after certain value of stress it would actually break. So this is a destructive test. Okay, and so once the broken pieces are assembled, okay, we can measure what is the total change length. Now this total change length would not be measured about the full length. It would be, it's not about 350 millimeters. It would be based on the effective length. You see that the higher diameter portion, the 12 millimeter higher diameter portion which is inside the two crosslets, that barely extends beyond the elastic point. But in the middle region, which is 10 millimeter diameter, that has substantial amount of plastic deformation, and that's where we want to focus. So when we would be measuring the percentage elongation, that is based on your effective length, and that is also not based on your extensometer gauge length. So the extensometer gauge length is there for measurement of the strain, but for the measurement of the percentage elongation, we would be using the effective length. Okay. So here we have already preset some of the load values, okay, because we already have the load data from the dial over there. So we can directly note the corresponding reading of the extensometer, left and right, and eventually taking the averages. Okay, and ultimately here are these columns are for you to do the calculations. Okay, the stresses, strains, and ultimately calculation of the Young's modulus from the the ratio of the stresses and strains, and then average Young's modulus, and so on. Several calculations are there. But one more thing, as I mentioned earlier, the working length of this extensometer is up to 5 millimeters. From 0 to 5 millimeters of elongation, we can use this extensometer. Now, as you might know, that the material has substantial elongation in the plastic region. Let's say if you are testing a ductile material, and then in the plastic region it will have several times higher elongation than in the elastic region. Okay, and when does the plastic region starts, or when does the plastic deformation starts? It starts beyond the yield point. Now what is an yield point? An yield point is a stress value at which the rate with smaller increase in stress there is a substantial increase in strain, or the gradient of the stress or the rate of stress is much smaller. So the stress strain diagram is kind of flat in the yield point. So there is the Hookean part, which is a linear part, then it becomes becomes flat for a small domain, and after that it starts developing stresses further. So the first region is the elastic region, then comes the yield point, and then comes your hardening region. Hardening is the region where the material regains its original stiffness. Okay, so the material is most stiff in its elastic region, and the stiffness kind of momentarily, I shouldn't be using the temporal term, it becomes the slope becomes flat at the vicinity of the yield point, and after that it again regains some of its stiffness, and that is the hardening portion where the curve again increases, the stress again increases. So now the thing is, we don't want our extensometer, which is a very delicate instrument, we do not want it to be subjected to plastic deformation. So so we only want to use this extensometer up to the yield point. So this instrument is there only for measuring the elastic strain. And once we know we have hit the yield point, we will remove the extensometer, and beyond yield point, we are not taking any measurement of the strain. We cannot, because we have already removed the extensometer. But we can still have the load be recorded from the dial, and therefore we can get the yield point or maximum load value or the break load. Again, what is the maximum load? We have shown two hands in the dial that gives you the force value. One that gives you the instantaneous load value, the other one gives you the maximum load value across the entire loading cycle. So that maximum load value is what you are supposed to write here. This says maximum load, and from that you are supposed to calculate the ultimate strength. And then at the breaking point also, that means when the material fractures, so the final stress value is the breaking point. So that you are also supposed to note. Okay, so that's with the extensometer, that's with the instruction sheet over here, and now we can directly proceed for the experiment.
2.5.
1.
5.
3, 2.
7.5.
4, 3.
10.
5, 4.
12.5.
5.5. 4, 5.
15.
7, 5.
17.5.
8, 6.
20.
9, 8.
22.5.
10, 9.
25.
11, 9.5.
27.5.
12.
ঘুরে যাচ্ছে, ঘুরে গেলে বলবে ইল করে গেছে। 2750।
12, 10. দেখ তোকে খুলে নিচ্ছি।
দাদা খুলো না, খুলো না, একটু দাদা।
হ্যাঁ এই যে রান করছে, হ্যাঁ এইটা
হ্যাঁ, এই করে গেছে।
এই যে করছে, ঘুরছে।
এইখানটা এখানে তুলে কিন্তু
ঠিক আছে, এবার ওইটা
So right now we have reached the yield point, and as we can see, we are developing rapid extension for
The yield
tiny
point.
things. So what we are doing is we are removing the extension. Beyond this point, we will not be attaching the extension. So the yield point value is 27.5 kilonewton. So from that you are supposed to calculate the stress. And this is what is marked as the yield point, where the curve has momentarily become flat, and now it is going for the maximum stress value or the maximum load value.
ভাঙছে, ভাঙছে, ভাঙছে।
Okay. So the maximum load value is
37।
37.
না 37 কি করে? 30, 35, 35,
36. 36.
36.
36 kilometer. And the braking load is
3250।
so this is where we have reached the maximum load value. Okay, and after that the spontaneously the material goes for failure. Okay, as we apply more and more elongation, the load for doesn't increase further and decreases from this point and ultimately causes a fracture. Now this load, this is where the fracture happened. This jerk shape happened where the fracture happened, and after that the load obviously becomes zero because there is the material has already broken and it cannot sustain any further load. is the broken specimen. Okay, and as you can see, it forms the famous cup and cone shape. So this one is a cone, and there you can see this hollow cup forming inside inside this rod. Okay, ideally the necking should happen in the middle of the specimen. Now, what is necking? While we are continuously loading beyond the maximum load value or the ultimate stress value, somewhere within the along the length of the rod, that means that this uniform 10 millimeter diameter portion, somewhere we are supposed to see the rapid reduction in the cross section. Obviously, because of the elastic and plastic deformation, cross section was gradually reducing, but somewhere we would see rapid reduction and eventually leading to failure. Okay. Now, the amount of reduction in the cross section is actually an indication of the ductility of the material. If the material is perfectly ductile, this portion would actually end at a point. But as you can see, it has not. So this has certain amount of brittleness into it. Also, one more problem. Ideally, if we do, let's say, a finite element simulation in ANSYS or Abacus, there you would see that that region where the cross section reduces to minimum, that happens exactly in middle of the rod. Okay, but in this case, as you can see, it has happened at a end. Okay, actually closer to the taper region. Okay, so it's still in the 10 millimeter diameter region, but closer to one of the ends. Okay, so this has happened obviously because it's not perfectly cylinder, it's not uniform everywhere, because you see it has been prepared through turning, and in turning usually the middle region has the higher diameter. So in this case what we have obtained is the maximum load we have obtained is around 55.5 kilonewton. Okay, so it has gone past 50 and then 10 marks, that is 50.55 and then another mark, so 11 marks. So 55.5 kilonewton is the maximum load, and from the cross section area you can find out what would be the ultimate tensile strength. Okay, so so the breaking point was around 32.5 kilonewton, and we have written down the information after the experiment. For example, the length after breaking is 194 millimeter. You might recall the original length was 165 millimeter, and after breaking the length has become 194 millimeter. Okay. So what length are we talking about? We are talking about the effective length, the length of the 10 millimeter portion. Okay. So that has changed from 165 to 194, and from that you can figure out how much is the percentage elongation. Both percentage elongation and the reduction in cross section is a measurement of the ductility of the material. The more the material is ductile, the higher will be the reduction in the cross section, and higher will be the change in the length. Okay, and also we have generated this graph. Okay, that shows you the value of the load versus the elongation. Okay, so that is there, and we have this broken specimen over here, and this is your instruction sheet over there. So we have written down all the data that you require, and on this side we have noted down the values of the different deflections from the load. So there are two columns. So in one of them we have noted down the left dial of the extensometer, on the other one the right dial, and this way we got the elongations within the elastic limit. And as soon as we encountered 27.5 kilonewton, we realized that we have hit the yield point. Yield point is where the extensometer dials show rapid change in the reading, although the load is only gradually changing. So that this flat region in the curve is manifested when we are doing the experiment. That flat region is manifested through such behavior. So that point is known as the yield point. And after that we have noted down the maximum load and also the breaking load.